Okay.
Hi, good morning, good afternoon, good evening. Hello, everyone. Welcome to the Geoscience and Geoenergy webinar of 13th of May. Sebastian and myself are delighted, pleased, and honored to host you all every week with a geoscientific and geoenergetic talk. And especially today is a very special day. It's Eid, as well as Ascension Day in Netherlands, and also it's Father's Day in Germany too. So it's a very special day to host a webinar. We hope all of you are doing great, are in good shape and healthy and happy. Today we have the pleasure, honor of hosting our dear friend and colleague Steffen Berg. Steffen is a principal science expert at Shell Global Solutions International in the Netherlands. His main research interests range from the fundamental aspects of multiphase flow in porous media, including pore-scale physics, digital rock inevitability, to CO2 sequestration and multiphase flow applications beyond subsurface. He holds a master's degree in materials science from Saarland University and a PhD in physics from the University of Mainz and Max Planck Institute for Polymer Research at Mainz as well in Germany. After a postdoc at Princeton University, he joined Shell as a research scientist. He's currently still with Shell, as I mentioned, also holds a visiting reader, associate professor position in the earth science and engineering and chemical engineering departments at Imperial College London. He's also chair of the Interpol chapter of Netherlands, Dutch Interpol chapter, also chair of Interpol Foundation and a council member of the Interpol, and he's quite active member in Interpol and providing enormous service to the community, and we are all grateful for all he is doing to the entire society in his role in Interpol. Please do visit his Google Scholar page to study his fundamental research outputs and papers. I can go through them all here, but please also, more importantly, get in touch with him in the case you have questions, you have mutually interested projects in mind. He's remarkably fast in response to scientific discussions through email. So he's one of those few scientists who are really active, and it takes very short period of time for him to evaluate a work project, a draft or something. It's so active and so communicative and reachable. So we are really delighted and grateful to have him as a dear colleague with us. And thanks to Steffen, again, one more time for graciously accepting to give this lecture despite having a sunny vacation day today. So it's public holiday in Netherlands. It's a pleasure to host you. And to the audience, please note, Steffen's lecture would last for about half an hour, like always, and followed by discussions. Sebastian will chair the discussion after the lecture. Do not wait until the end of the lecture to post your questions in the chat box. Please do post them anytime you feel appropriate. They may trigger other questions by the audience as well. Without any further ado, Steffen, the stage, bandwidth, the screen is all yours. We are very much looking forward to hearing your lecture today.
Well, dear Hardy and dear Sebastian, thanks a lot for having me today and giving me the opportunity to present some of the latest insights in multiphase flow physics. Also, really thanks for the very kind introduction and all the praise. I feel almost like embarrassed if you hold me accountable to that. Well, so let's get going. I want to start with actually acknowledging that there are actually various people involved in this work, colleagues from Shell, from the University of New South Wales. Actually, go to the laser pointer. James McClure from Virginia Tech. Maya Rücker, in the meantime, moved on and is an assistant professor at Eindhoven Technical University. You probably have seen her presentation. And then there are some collaboration partners from the University of Mainz. So today, the topic of my presentation is multiphase flow, and I start with Darcy scale models and a quantification of uncertainty. And then we run into an interesting observation, which ultimately brings us to the question of energy balance in multiphase flow. So here, just as a brief introduction, multiphase flow in porous media is really relevant for a lot of situations in geosciences, but also in chemical engineering. So we have the vadose zone, we have CO2 sequestration and hydrogen underground storage, hydrocarbon recovery, contaminant hydrology. All of these are evidently subject to multiphase flow in porous rock. But then there are also situations in electrochemical and electrocatalytic devices like fuel cells and electrolysis, which are not so evident multiphase flow, but these devices contain gas diffusion layers. And the transport in these gas diffusion layers are ultimately also controlling or impacting at least the rate and the efficiency of these devices. And so the flow physics in these devices is also important, and in particular the CO2 sequestration and hydrogen storage and fuel cells immediately give a relation to the question of energy balance in multiphase flow, because these are really all related to the question of energy efficiency. And then there's ultimately also, like in every day, we see salt crystallization in sandstone buildings, and there's also multiphase flow physics involved. So how do we describe multiphase flow in porous media? Let's start with single phase flow, and there we have Darcy's law that can be derived from fundamental principles, but it was introduced actually in a more phenomenological, empirical manner. We have a flux of a phase which is proportional to the negative pressure gradient, and it's inversely proportional to the fluid viscosity, and the constant of proportionality is the permeability. If we now go to multiphase flow, the most common description of multiphase flow is a extension of Darcy's law to multiple phases. So that is not a law anymore, it's a phenomenological extension, and here we are basically substituting the fluxes by for single phase to the flux for each phase. We have a pressure gradient for each phase, we have a viscosity for each phase, and then we introduce a phenomenological parameter called relative permeability, which is accounting for the fact that when two immiscible fluids share the pore space, they hinder each other, and that has to be taken into account. So depending on the saturation of one versus the other fluid, so here I have like wetting phase saturation plotted, the relative permeability of the non-wetting phase decreases and the relative permeability of the wetting phase increases. And the process is hysteretic, so we have different relative permeability curves for drainage and for imbibition processes. So depending on whether the wetting phase is decreasing or increasing, we have different curves. And the same holds for the pressure difference between the two fluid phases. Yeah, this is described by the capillary pressure saturation function, which is the upper curve for drainage and the lower curve for imbibition. It depends on many different things, for instance, wetting properties of the porous medium, but also the direction of the saturation change. So two-phase Darcy is really the most common approach that we use, at least in the petroleum industry, but in also many other areas of science and technology. But it is not the only model that is around for multiphase flow. There are much more rigorously derived models. For instance, the model by Hassanizadeh and Gray. Then there is a model by Gray and Miller. These two use very rigorous thermodynamic frameworks. Then there are models introduced from the group of Rudolf Hilfer. They are phenomenological in some sense, but they account for the fact that they are connected and disconnected phases for wetting and non-wetting fluids. And what these models have in common is that they all have these hydraulic conductivity parameters. So in two-phase Darcy, this is relative permeability. And in the other models, sometimes it's formulated as a resistance factor, which is then proportional to 1 over the conductivity. And depending on the complexity of the model, there can be multiple of these factors. And also depending on the model, for instance, here, when we look at the most simple version of the Hassanizadeh and Gray model, we can already see that the interpretation of the hydraulic conductivity factor changes, because it's not just the hydraulic conductivity anymore that is embedded into the relative permeability in two-phase Darcy, but it also contains inevitably other terms from the model. So if you basically say, well, ultimately we describe the same kind of phase flux, that means that these different terms have all to be lumped into this relative permeability product. So we are facing basically a situation where we have different flow models, and they have different interpretation of what this hydraulic conductivity means, but they also have really different functional relationships. For instance, here it would mean that relative permeability is dependent on saturation gradient and many other things, which in the original two-phase Darcy was never really articulated that well. So the question is now, which model is really the right one? So we can do very dedicated targeted experiments, but we can also go to an approach that you would use, for instance, in astrophysics. If you ask yourself which is the correct model for gravity, and we have an observation, and you ask basically the question, what is the probability that the model describes the data? That ultimately leads us to the question, what is then the uncertainty when we try to match the experimental data with the different models? So before you get all overexcited, I'm not going to tell you which model is correct. We are actually running into very interesting other problems and questions while we were on a journey to explore that. So we have here, in order to assess, so what we basically need is a workflow to assess the uncertainty of relative permeability in a flow experiment when we describe it with a model. So we make heavily use of Python and the optimization toolbox. We have a two-phase flow simulator in one dimension. There are different codes involved here. One is our in-house reservoir simulator. Then we have a native Python code with the number just-in-time compiler, which makes it really fast. So you can do a lot of more things when you do that. But there's also, for instance, the Dart simulator from Delft University, which is open source. It has Python bindings. It's relatively convenient to use in combination with that as well. So what we do is we do a flow experiment. We then describe the chi-square, which is the sum of all the squared differences between the model prediction and the data, and we minimize this chi-square, and then we match the experimental data. But we can do so much more. We can now make cuts for the chi-square landscape in parameterized versus the model parameters, for instance. And then we can explore whether the model is actually in the end providing us a unique match. And ultimately, we get then, when we look at all these the uncertainty, which you can assess, for instance, from the shape of these minima, which is described by the covariance. You can also run a Markov chain Monte Carlo, which is possible because just-in-time compiler makes it really fast, and get uncertainty ranges of relative permeability. And then we can ask the question, is now one model describing the data better than the other? What does it really say about the uncertainty ranges? Before you get excited, we're actually not really getting to compare other models. There is a lot more fundamental things that we are running into. Okay, so let's test the workflow. We do here a very, very simple test. This is the one-dimensional unsteady state displacement. Capillary pressure is 0 here. We use synthetic data just to test the workflow. And we get already very much surprised. So we basically use a synthetic data curve. Here, this is the dotted relative permeability, dashed relative permeability curves. We forecast production curve and pressure drop of a unsteady state flow experiment. We add some noise, and then we apply our inverse modeling workflow. We get a very good match, but we don't recover the ground truth. We don't recover the relative permeability that we put in. And depending on which constraints you apply, you get slightly different matches, but ultimately the relative permeability is not recovered exactly. It looks close, but it's not recovered exactly. So then you wonder, like, what's going on here? Is there a bug in our code? What's wrong? It actually turns out when you look at these cuts through the chi-square landscape, and we here plot, for instance, the plane. This is the endpoint water relative permeability versus the residual oil saturation. And we basically calculate each point here. So we don't minimize the chi-square, we calculate the chi-square for each parameter value. And we see that, so dark means a small error, and bright means a large error. And then when we look very carefully, you see basically multiple local minima. And the blue point is the starting point of our optimization. The green line is the trajectory that the optimizer is using, and the red point is the final convergence, and that red ellipse is the error ellipse. And you see that in some cases, it's not even, for some parameters, it's not really converging to the minimum. So there is a fundamental problem. The biggest element here is that you have multiple local minima. And you see this also when for a certain choice of parameter sets and constraints, I can make a contour plot in 3D. So the colors now represent the chi-squared, and I see here 4 discrete local minima. And then, of course, it matters from which point you start, to which minimum you converge. And on top of that, these local minima are sitting in a very elongated sort of valley, which means that with very little cost, you can basically assume almost any valley, any point in this valley, which means that certain parameters are not very well defined by the model. So I have here an example. This is now experimental data. This is an unsteady state experimental experiment, and we apply our workflow, and then we choose different starting points for our minimization, and we basically reach a different local minimum for each starting point. So in order to assess now different models, this is completely useless because the inversion is non-unique. In order to make this a little bit better, we need to use more experimental data to constrain our solution. So we are using now so-called bump floods, where we increase the rate in steps of factor 2, 5, and 10. And then we start seeing, when we use this additional experimental data, we see a much better constraint of our solution. And also we seem to be converging pretty much always to the same local minimum, but it's still not perfect. Yeah? So the problem is still non-unique. It's still non-unique, but it's a little bit better than, so the bump flood made it a little bit better. So let's switch gears to a different type of experiment, which is much more controlled. So the steady state core flooding experiment is much more controlled. So this is the kind of setup that we would use. We have our rock, our porous medium. We inject water and oil simultaneously, and we monitor the saturation in the rock with X-ray, and then we change during the experiment the ratio of water and oil, and in that way change the saturation, and in this way then measure at each fractional flow different pressure drops. We measure different saturations with the X-ray, and so for each plateau we get then a relative permeability point. The relative permeability point is computed ultimately using the flow model. So we're using the pressure drop, and more specifically, we use the average pressure drop. So this is something important to keep in mind, and because I will come much later towards the end of my presentation back to that average, because there is some problem with taking this average. So that is the experiment, and we can now apply the same inverse modeling workflow. And here we are also using the capillary pressure saturation function, which has been independently measured as part of our inverse modeling. We include that in the match. Yeah? And then we encounter something really interesting. So we have here these pressure drops, and the red curve is the model, is the final convergence of the model. And we also have 2 bump floods at higher rates at the end of the experiment. Now, for our interpretation, we use 2 different relative permeability representations. One is the Cori representation, and one is the LET representation. I don't want to really go into detail now and explain the exact difference. This is all explained in our recent papers. The important message here is, when I use the Cori representation, I don't really match the experiment that well. And I also have here a discrepancy, and I'm not matching here my capillary pressure curve very well. In particular, there's a different residual oil saturation, which I finally match. And the resulting relative permeability function is different than if I would basically just do a manual match and match each plateau individually, not using any smooth representation of relative permeability. Yeah, I'm doing it basically point by point. If I use, on the other hand, the LAT representation, I get a reasonably good match of my experiment, also of the capillary pressure curve, and I have a match ultimately of relative permeability, which is not too different from a manual match. And that looks a lot more consistent. So the take-home message here is that it's not only the flow model that matters, it's also the relative permeability representation that matters. And before, you can't get really a good grip on which relative permeability representation you should now be using. It is hopeless to ask the question which the right flow model is. Okay, I'm jumping a little bit ahead here. The interesting thing is, because you could say, why do you use any relative permeability representation at all? Do it point by point, as you would do it manually, basically, by doing a manual match. Well, the thing is, when you play it through, and here I'm using a Markov chain Monte Carlo method it's basically sampling the whole parameter space in an intelligent manner to assess the true uncertainty and compare that with doing the manual match and then fitting, for instance, a well-perm function through. You see on the left-hand side, when I do the manual match first, and then I get like an experimental error bar, and then I do a least square fit with like a well-perm function of my choice. Here it's LET to stay consistent. The shaded regions is the uncertainty region. If I fit the flow model directly to the data with the inverse modeling, you almost don't see the shaded region anymore. So the uncertainty is significantly smaller when I really use the full inverse modeling workflow. So that seems to be the more logical way to go. But there are still issues, because when we look now, let's say the LAT function seems to be like the best match that there is at the moment. But when we look at the residuals, so this is the mismatch between, in terms of pressure drop, between the model and the experimental data. And here we draw in the dashed black lines the one standard deviation interval. We still see that there is a lot of mismatch, and the mismatch is much bigger than one standard deviation, and it's systematic. And there seem to be two components. One is like a really systematic trends jumping up and down here. The other one are like these spikes and fluctuations. So one thing is clear. There is still something else that the model doesn't really describe. There are really systematic mismatches. The statistics of that would be non-Gaussian, and which when you basically know a little bit what people in astrophysics do, systematic errors usually means that there is something in the model simply missing, or you miss something else. So I'm going to focus now not on really these jumps, but I'm focusing on these fluctuations. What are these actually? Are these just pore-scale events? Because I have actually published conference papers where we speculated that these were pore-scale events, and at first glance it looked like it. But let's zoom in. This is now a different experiment, different experimental data than the previous one, but conceptually the same. It's a steady-state flow experiment. We use Fontainebleau sandstone. We try to rule out as many influence factors as possible. So we use decane as oil phase and saline brine as water phase. So we exclude any kind of emulsion formation, so as many possible experimental artifacts as we can. And then we change the fractional flow. So this is a drainage experiment. We start with 100% water, and then we slowly decrease the rate of water and increase the rate of oil. And here the blue curve is the pressure drop as a function of injected pore volumes. And then we see there are these very small wiggles, but then at certain fractional flows, there are really large fluctuations. So what in all world are these? So in order to, and these fluctuations are not only in the pressure drop, we see them also in saturation, and we see them in electrical conductivity. Now you may ask the question, why aren't they the same kind of trend as pressure drop? Yeah, these experiments haven't really been designed for exactly this purpose, and we sample pressure much quicker than we sample saturation and conductivity. The pressure is sampled at 1 minute intervals, and the saturation is sampled at like 8.5 minute intervals. That can explain to some extent why these are not completely in sync. Okay, now in order to look a little bit more detailed, we go for each fractional flow plateau. subtract the baseline from the pressure signal and the saturation and only plot the fluctuations. And then we also make a histogram. So for the early fractional flows where you have very little fluctuations, you see that the histogram, when you really zoom in, is perfectly Gaussian. So here you could say the interpretation of this could be really noise, random noise, could be instrumental noise. But when you go to some other fractional flows like this, the one where the fluctuations are very high, the fluctuation magnitude is much higher, but also the histogram is non-Gaussian. Yeah, it's almost bimodal. In certain cases, it is perfectly bimodal, and the fluctuations are perfectly periodic. So why is this happening? Periodic fluctuations, that doesn't sound like random noise at all. So what is causing this? So when not only plotting the pressure drop as a function of time, but actually looking at the saturation profiles as a function of time, because we monitor that in our experiment as well. That then reveals in this contour plot, I have here the position along the core. The saturation is encoded in the color with this legend here on the right, and I plotted here as function of time. You see now that you have banks of higher water saturation moving forward. So they are actually traveling waves. They are periodic. They occur for certain fractional flows, not for all. And they seem to be moving at constant velocity. But the velocity depends on the fractional flow. So why? That is now the question. What is actually causing this? Now, if we see, the first question is this a Darcy scale phenomenon? Or is this something else? If it is a Darcy scale phenomenon, it needs to obey fractional flow physics. So I don't want to really drag you too much into fractional flow physics. There is actually a lot of literature on that topic. And the bottom line here is that you need to consider when you have a moving bank, you have like an edge that is, for instance, strainage, and you have like a leading edge, which is strainage, and you have like a following front, which is then imbibition, or the other way around. So you're dealing ultimately with hysteresis solutions. And these have been worked out in the literature. There are quite a number of papers on that topic. And you see basically that there is a fractional flow solution, and it can be explained. But then why does it actually form these? Why is this happening? So one way of looking at this is that you need to take the fractional flow solutions, the hysteresis formulation of the equations, perform a perturbation analysis, and check whether the solution is unstable against perturbations. The perturbations could be pore-scale events. So you need to do a linear stability of the flow model and check that. I'm not going to do that here because this is awfully complicated, and this is something that if somebody of these authors, for instance, or Pavel Betrikovetsky is listening, that is your playground. You're very much invited to do that. I'm doing something else. I'm coming up with a total mobility argument. So I'm now calculating the total mobility for the flat saturation profile and for the saturation profile with the moving banks. And it turns out that in a certain saturation range, moving banks have a higher total mobility than the flat saturation profile. And that would explain why these strong fluctuations, which are associated with moving banks, occur in a certain saturation range and not in another saturation range. It basically means that for the same pressure drop, you transport more flux. And that is what the system then chooses. That is what nature chooses to do. So looking at the pore-scale, because we said, well, these banks, they need to be triggered by something. It's maybe an instability that needs to be triggered by something, and that could be pore-scale events. So let's do a pore-scale flow experiment. So this is now a micro-CT flow experiment. It is a fractional flow experiment, basically also like a steady-state experiment. The sample is just much smaller. We co-inject water and oil, and then we monitor the pore-scale fluid distribution. And we see different flow regimes. There is, for instance, the connected pathway regime. It still has some fluctuations, but ultimately it's just fluctuating a little bit here and there. It's maybe like some of these fractional flows where we didn't see strong fluctuations would be maybe equivalent to what we see here. But then we have what we at the time called ganglion dynamics, and this is very, very strong fluctuations. And when we plot that here as a function of time, for instance, when we plot the pressure drop as a function of time, we see here pressure drop events. We also see saturation changes, which are approximately same magnitude as the ones we have seen in our Darcy scale experiments. So perhaps that is actually the same effect, only what looks from the pore scale as a cooperative filling events would look at a larger sample as a moving bank. Only the pore scale experiment is way too small to basically see the moving bank. This is smaller than the edge of the bank, so you wouldn't see the bank. But perhaps this is just the bridge between what happens at the pore and what happens at the Darcy scale. What is pretty much clear is that these large fluctuating events, they contain hundreds to thousands of individual pore filling events. So if we want to learn something more about the trigger mechanism, we have to still focus even more to what is happening in individual pores. And this is old experimental data. This is also old knowledge in some sense. But we are coming now a bit to the topic of energy dissipation. Because when you look at individual pore filling events like Haynes jumps, where the pressure drop follows like a zigzag curve, like a sawtooth function, where you first kind of increase your pressure drop until you exceed the capillary entry pressure and then rapidly fill your pore. You can ask the question about the energy dissipation, because these filling events, they dissipate most of their energy. Because at the end of the filling event, the fluid comes to complete rest, and all the kinetic energy is converted to some extent into a new interfacial area, but also it's just converted to heat. And when you look at this in detail, there's multiple independent experimental data on this topic. We find that roughly 2/3 of the energy gets dissipated in strongly water-wet rock. And when we also look at what is approximately the energy scale, what is the magnitude, how much energy is it that gets dissipated? For typical sandstone rocks, we get in the order of magnitude 10 to the -5 to 10 to the -7 joules, and that corresponds to a wide range of energy in KT. It's many orders of magnitude higher than the thermal energy, which basically means that we are talking here about non-thermal fluctuations. And now we are getting about into the same language that our colleagues from Pore Lab are using, because they are experts in non-equilibrium thermodynamics. And perhaps this whole problem of multiphase flow is ultimately not so much a flow problem, but a thermodynamic problem. And it's actually maybe something really in the domain of non-equilibrium thermodynamics. Okay, we are kind of getting very slowly into this topic, and let me do one hypothetical thought experiment. What if we are not flowing the fluid through these jump events, but what if it was actually something smooth that didn't have these dissipative events? What if we just use two-phase Darcy and calculate the viscous dissipation, the work against the pressure volume work, which corresponds ultimately to viscous dissipation in a hypothetical connected pathway flow regime, and then get a certain amount of dissipated energy. When we look, on the other hand, at the energy dissipation of all these jump events, we get here an energy dissipation which is roughly 2 orders of magnitude higher. So when we look at the ratio of these, this is basically a factor factor 200 higher. So the actual dissipation that happens is a factor 200 higher than what two-phase Darcy makes us believe. So what's going on here? What's wrong? Well, remember when I told you that we measure the relative permeability from the average pressure? That basically means that we have averaged out all of these things. And that is ultimately explaining the discrepancy. Admittedly, this is kind of an extreme case. It can be smaller, but in order to really do this more properly, I actually discussed this with James McClure, and then James, as a proper theoretician, actually said we have to do this properly. We have to develop a proper formalism, and the key is, I don't really want to bother you too much. We calculate ultimately the entropy generation rate, and has different terms. These are the terms that basically come from two-phase Darcy. Then there's capillary pressure dynamics, but then there are also the fluctuation terms. And these come into play when you apply an averaging operator over space and time. That's the key. So we at the moment, there are two preprints where you can look this up in detail. The interesting question is now, do these terms actually average out? Because these represent the fluctuations. And that is exactly what we are missing in two-phase Darcy, when we just average over our pressure drops, and then it doesn't enter the relative permeabilities anymore. So this amount of energy dissipation does not enter the relative permeability in our two-phase Darcy formulation. So let's look at the experimental data. We have here different averaging intervals, and you can already see, and in the histogram, in the fluctuation histogram, you can already see how going from 16-second averaging to 128-second averaging, how much it actually reduces the magnitude of these fluctuation terms. So you can see that averaging is indeed reducing the magnitude of these fluctuation terms, but the question is still, do they really average out? Can we just assume that this would always happen? One requirement is definitely that it needs to be a stationary problem. So in steady state, when everything is ultimately time independent, like you could potentially expect that these fluctuations do average out. But it requires a reasonably long time interval. When you look, for instance, at the standard deviation of these fluctuation terms, it might require a very long time interval over which your flow really needs to be steady. So slowly trying to come to an end here. So the take-home message is, when you rewrite the entropy generation rate in the so-called flux force form, you would need to demand that these fluctuation terms disappear in order to arrive at a Darcy type flow equations. So that is somehow the actual upscaling step, going from pore to Darcy scale. And if these terms don't disappear, it would basically mean that the two-phase Darcy formulation does not fully cover the energy dissipation, the true energy dissipation. And that might be something really important for certain applications when energy dissipation really matters. There is one more aspect that you need to consider, even though you could say, naya, maybe in stationary problems, everything averages out. Naya, ultimately, we are talking about thermalization. What does averaging out really mean? We mean ultimately you need to convert all your dissipation into thermal energy and homogenize it, and the homogenization is governed by diffusive exchange, diffusive transport. And then you can ask the question, are our pore-scale events actually faster than the mixing of diffusive transport? And when we look at this for typical Haynes jumps, we have here the distance, and these are the trajectories of different Haynes jumps in experiments. We see that at early times, diffusion is beating everything, but at late times, it is actually not mixing. Which is then basically a problem for ergodicity. It basically means that at late times, the ergodicity breaks. And then that opens the question about, like, is the system in the end really thermalizing? Is it really ergodic? Is it really averaging out? It's still a bit of an open question, but we are pretty much at it in order to solve that. It's rather I would say the beginning than the end. There's really exciting things. But let me come to conclusions now. We see basically when going really in the multiphase flow problem, it is not enough to basically say I have sort of, it's a flow problem and I have sort of capillary energies and then I sort of average and get somehow to the Darcy scale. There is there's much more physics involved in this. Ultimately, you need to consider mixing at the molecular scale. You need to consider the different energy scales, which phenomenon happens at which energy scale. Is it really averaging out? Is it not averaging out? And these are still open questions, but I think now we found the right way of looking at this, and we have almost the toolkits now ready to start looking at this. So we started from asking the question about constitutive flow models for two-phase flow. We found it's often non-unique. We found fluctuations. These are not noise. We have seen traveling waves. They can be explained by fractional flow solutions. At the pore scale, there can be cooperative events. They dissipate energy, and they average out only if they are stationary. But the transition from the pore to Darcy scale is ultimately defined how these fluctuations average out. And that is really an exciting topic to study in the coming weeks, months, I hope not years. It feels like we are kind of now, we can at least articulate what actually really needs to be done in order to really upscale multiphase flow from the pore to the Darcy scale. Yeah, and with that, I would like to close and acknowledge a couple of more people that are involved. Also, Apostolos Georgiadis and Holger Ott, who is now the chair of petroleum engineering at the Montana Universität Leoben, was involved in some of this work, and all of that was really a truly cooperative effort. Thank you very much, and now I'm very happy to answer questions.
Thanks a lot for this very inspiring and very engaging talk, as always, Stefan. We are not surprised, but it was again another very interesting talk. I see already a lot of questions posted. We have also questions, but the audience have the priority all the time. So Sebastian, please go ahead.
Yes, also big thank you from me, Steffen, for a great talk. Really, really interesting, and know that we've run workshops 10 years ago. And I remember some of the talks from Majid Hassanin-Zadeh about upscaling and from pore to Darcy scale. It's really great to see the work that you and your colleagues have done and how it has progressed. Yeah, plenty of questions. The first one is from a certain Florian Doster you have cited, mentioned there. He starts, obviously, fantastic talk. And he wonders, should you pick an optimizer that gets the global minimum when you talked about the chi-squared maps and how you're getting trapped in local minima? Would different optimizers, search algorithms help you?
Yeah, that is a good question. And these are, first, thanks for like all the praise and all the fantastic comments and all the good questions I'm seeing already here. So sorry when I'm turning my head, I'm looking here on another computer on the questions a bit. Yes, you could say I need just a better optimizer. We are kind of converging a bit more to that we should not use an optimizer at all, but we should just basically use a better Markov chain Monte Carlo sampler. We are at the moment working on this already. The one that I used is the MC package, which is just like a change of one single line in the LM fit in Python, but they are a lot better samplers. My colleague Harm Dyke tested something like 10 of them, and nested samplers are a lot better. So computers are not fast enough. This runs on a laptop. And just okay, the MC took 10 hours to run with 20,000 iterations, but I think with the nested samplers you can probably do this in a matter of minutes. And then you shouldn't use any least square optimizer at all. You just use Markov chain Monte Carlo and sample your whole parameter space. You do have to be careful, and not all of these are made for multiple minima. Yeah, nested samplers from astrophysics are sometimes good to use.
Okay, continuing on the theme of the samplers or optimizers. So Po-Wei Wang again also says, very inspiring talk, thank you. The question is, do you consider other divergence measures, for example, the KL divergence, relative entropy for the minimization problem between model and observation?
I think the first step, yes, a good question, and you can pursue the whole problem more from the direction saying I have a model and I want to have multiple minima, and it's just an optimization problem. My take on this is a bit different. Our starting point was not to find the optimum. That was not the objective. The objective was to find the uncertainty. Because that is something that you don't really get when you do it by hand so well. Yeah? Using an optimizer and finding a optimum and then using the covariance matrix, that was a bit our objective. But the question is much more, when you see that and find that you have systematic errors, it gets you immediately back to the question. Now you have an uncertainty assessment and you can ask now, is the model within, you can use methods like Bayesian evidence and say, does the model actually describe the data? And or do I need to already start making my model more complex? So before sort of abandoning two-phase Darcy, you would first actually have to do the same exercise with a hysteretic model, with a hysteretic version of two-phase Darcy. The crux in all of this is that as soon as you start using hysteretic models, you need to define, for instance, the scanning curves, the hysteresis model in itself. All of this is introducing more parameters. And then you introduce also cross correlations between these parameters, and you become very quickly underdetermined. We have seen this already in the LET model. So LET fits the data better, but you see I haven't described this yet, but it's in one of the papers that in the computers and computers and geotechnics paper. You see that you get cross correlations of parameters. So as soon as your model is over parameterizing your problem, you get these strong cross correlations, and then you need additional experimental data to constrain it. And that is a little bit the crux that we see at the moment.
Okay. Yeah. Thank you very much. I was hesitating because I had some questions myself there, but the questions from the audience are coming in very, very quickly. So stick with the audience questions. Leda is asking the following question. She says, "Thank you for your talk. Will the same phenomena happen in gas-liquid multiphase flow?" You talked about hydrogen, for example.
Well, fantastic question. Gas systems, which I haven't really talked about today, but we have done also quite a bit of research recently on gas systems. And then there is also really the groundbreaking work of Kirk Su, who has written nice papers on ripening and anti-ripening. We get to the impression that capillary equilibrium in gas systems means something entirely different than in two-phase flow with like immiscible liquids. So one aspect of gas systems is that you have a stronger viscosity ratio. You have potentially much more unstable displacement. We have seen, or my colleagues from Imperial College, for instance, Catherine Spurin, has seen that gas systems have much more intermittency. So it is a matter of viscosity ratios, but then we also see that diffusive exchange in gas systems contributes very largely to what we mean by capillary equilibrium. It's actually not a capillary equilibrium anymore. It's more like a chemical potential equilibrium you converge to in the end. Lots of questions in gas systems deserves basically an extra talk, to be completely honest.
We have slots available for 2022, and we're happy to invite you back then.
Sure, absolutely.
Bill Rossen asked the following question. Interesting talk. For a really simplistic takeaway, does accounting for energy dissipation in the pore-scale jumps mean, in a sense, relative permeability is reduced?
So the problem basically is that two-phase Darcy represents a mass and momentum balance, but not an energy balance. And potentially, depending on the situation. This is at the moment how it looks. So I don't want to say, don't quote me on this yet, that two-phase Darcy is not in agreement with the first law of thermodynamics. It never was meant to be. It is simply a mass and momentum balance. If you want to account for the energy dissipation, then you would, when you just use two-phase Darcy, you would underestimate the energy dissipation, depending on your situation, potentially significantly. That has to be investigated in more detail, in more situations, in more test cases. But simply your relative permeability has averaged out these pressure drops. So yes, it would become basically smaller in that sense. But if you ask for an average momentum balance, then it seems to be appropriate, because it does describe your flux pressure drop relationship using the average pressure drop. But it does not account for all these like displacement events moving a little bit back and forth and then coming to a standstill again and dissipating energy by doing that. That is not contributing to average transport. That's the thing. So the momentum balance is covered, but the energy balance is not. The average momentum balance is covered, sorry.
Continuing, you mentioned energy dissipation. So I picked Yuang's question. Since energy dissipation takes time, would this indicate that Darcy's law needs to be modified to reflect such behavior? So you started commenting on this.
Yeah, so there's always the question, how would we have to modify the Darcy equation and so on? And there are the classical approaches from Hassanizadeh and Cray and Miller and TCAT, and there are more around. Yeah, I hope I haven't forgotten anybody. Yeah, shame on me, but there are more around. And the thing is that these approaches typically assume that you are already at an REV scale, and all of these fluctuation effects have averaged out. And then they apply rigorous thermodynamics. Yeah, like they use an entropy argument, like a local, global equilibrium, thermodynamic equilibrium argument to close the equations and arrive at constitutive relationships. We feel that the whole physics where it actually happens, where the transition from pore to Darcy scale happens, is exactly at the point where these fluctuations do average out or maybe don't average out. And then we haven't fully written it down yet, because for relative permeability, there are still more things to consider. At the moment, we are just looking at an energy balance. Relative permeability would be then the next step. There's also the argument about the whole topology. So how am I doing in time? Okay, so the story basically goes like this. You probably have seen Ryan Armstrong's talk on these Minkowski functionals.
Yep.
What we were actually trying to do is, when you say, okay, we understand what the state variables of multiphase flow are, all you basically then need is the partition function, and then you can calculate your thermodynamic averages, and you're done. This is what you would do in classical thermodynamics. This is what you would do in the ideal gas equation. How you derive the ideal gas equation from molecular gas kinetic theory. The problem with that is that before you can calculate the partition function, which is statistical mechanics, you need to do first the classical mechanics approach to calculate your force balances. And when we go through these displacement events, we see that the discontinuity of the Euler characteristic at displacement events propagates into the Euler-Lagrange equations. So they become discontinuous, they become non-differentiable. And that was the moment when we kind of said, well, we don't know anymore whether that whole formalism is still applicable for non-differentiable functions. That was the moment when we thought, let's completely look at this differently and look at the fluctuations and ask more from a non-equilibrium thermodynamics point of view that these fluctuation terms disappear. And that is what we believe at the moment with our knowledge that we have right now, that actually marks the transition to the Darcy scale and would open potentially the route to derive the constitutive relationships.
Okay. You mentioned fluctuation, Steffen, and a couple of questions on that topic. So start with Julien's first. Great talk. Is there a threshold capillary number under which the fluctuations will average out, or is that independent of capillary number?
There has been done a lot of work in Martin Plant's group, and also in the colleagues from PoreLab in Norway, like Alex Hansen, Signe Kjelstrup, and many colleagues. They have observed, so they use sometimes slightly different terminology. So we started using terms like ganglion dynamics. Then there's intermittency. We are still not 100% sure if it's exactly the same or something slightly different. But they have observed that these discontinuous pore-scale fluctuation events are strongly dependent on capillary number. There's also a regime, which I think Afram and Payatakis would call like drop traffic, where the relationship between pressure gradient and flux is nonlinear. So at low capillary numbers, you have a linear relationship. Then at intermediate capillary numbers, you have a nonlinear relationship. And then this two-phase Darcy business doesn't apply anyway. And then at high capillary numbers, you have again a linear relationship, but there you have enough viscous forces to force your non-wetting phase you're completely overcoming capillary forces. You're really in the viscous limit. What happens depends also on viscosity ratios, and there has been quite a bit of work from the Imperial College group to map that out properly. Yeah, so look at the papers of Martin Plant. They have described this in more detail.
Thank you. Hassan Mahani has a question. Great talk as always, again on pressure fluctuations. The pressure fluctuation is also related to the way we measure the pressure drop over core in the lab. Cannot measure pressure of both oil and water phases individually. We measure pressure of the most continuous phase. So can you comment on that?
Yes, that is absolutely true. And it is already showing that the phases are not continuous all the time, right? And that is already the first learning that we basically get from this observation, which is actually not always true. There can be situations where both phases can be continuous, and that depends on wetting properties. I believe Martin Plant presented some of this already in his presentation. There can be certain configurations where you have bicontinuous interfaces, and then you have both phases continuous. But it's true in these steady state experiments, but also in any fractional flow experiments, you don't know for sure experimentally over which phase you actually measure your pressure drop. Of course, you could argue maybe the fluctuations are basically locally induced, where you measure your pressure drop, but then we also measure the pressure drop over the flow lines. And you would assume that even if your local pressure tap is sort of sometimes facing oil and sometimes facing water, at some point you should be able to measure an average, and that doesn't seem to be the case.
Okay, thank you. I'm going to take one final question, and I'm picking one of Florian's questions again. He says, "Repeat myself, fantastic work, Steffen. With respect to your last comment on the diffusive length and loss of ergosity, do I understand correctly that there are sort of non-local interactions?"
Yes. So maybe one word about ergodicity, just to get everybody on the same page. In equilibrium thermodynamics, for instance, when you derive the ideal gas equation from the gas molecular kinetic theory, sort of from the Maxwell-Boltzmann velocity distribution, there's a certain, so what we measure then at the continuum scale is the ideal gas equation, which is pressure, volume, and temperature. So if you want to know what the temperature is, we need to calculate a thermodynamic average, and it would be primarily a time average. But often, in order to calculate things, we are not using time averages, we're using ensemble averages. And it boils down to the question, are these averages all identical? Is like a space, is a time, and is an ensemble average the same? And that does not seem to be the case. If you, for instance, imagine that you randomly distribute oil in your porous medium, it is different. You would reach pores that are in normal displacement processes never reached. And it also then raises the question, why is that? One of the reasons is that the energy scales of capillary displacements are many orders of magnitude higher than the thermal energy scale. What I described, that basically means you cannot just heat up your porous medium and you have enough thermal fluctuations, thermally induced fluctuations, that would allow you to do capillary displacements. You basically need 10 to the 5 or 10 to the power of 15 Kelvin to do that. Yeah, so you basically melt your porous medium before you do that. So thermal fluctuations cannot induce these capillary events. And that brings us down still to the question about like mixing of states. And we know that at least when we generate heat because of a Haynes jump, that generated heat is doing thermal diffusion in your liquid, which is associated to molecular movement. Of course, on the capillary scale, these systems are coupled via pressure waves, for instance. And there it is possible to induce ganglion dynamics by having, for instance, capillary waves along interfaces, which at some point exceed the velocity of diffusion. And that is one of the reasons why you see that the system at some point, the ergodicity breaks down.
Thank you. Thank you very much, Steffen. I think my time is up now, so thank you again for really great, really fascinating talk. Thank you to our audience for the many, many questions, and Steffen for answering them in such great detail and diligence. Also, thank you for taking some time out of your day off today to give your lecture. So, and with that, over to Hardy for some announcing the finals, the next speaker.
Yes, thanks a lot, everyone. The next speaker is Professor Catriona Eltman from the University of Edinburgh. She's going to talk about geological storage of hydrogen for decarbonization. And she will give especially an update of their project at the University of Edinburgh, which is called HyStorPore, Hydrogen Storage in Porous Rocks. So until next week, the same time, 4 p.m. Central European, 3 p.m. British time, 7 a.m. California. And I hope we soon go to airports and fly everywhere. Stay happy, healthy, and tuned. And please tune in at the right time for the talk on hydrogen storage. Thanks a lot, Steffen. It was great to see you first live and also to attend your talk again.
Well, thanks for having me.
Sure.
Thank you. Thank you,
Bye-bye, everyone.
Bye-bye.
Bye.